Today I'll discuss the most misunderstood concept of physics, that is about entropy, and Boltzmann's struggle with the second law of thermodynamics. On one hand, entropy always increases, we say and learn, while on the other hand, Newton's law is reversible. Entropy is a hidden information. Boltzmann's law deeply affected every area of science, but it did not solve the problem that Boltzmann originally set out to conquer. Why there is an arrow of time? Why time is a one-way street? Modern developments in cosmology makes this puzzle more puzzling, and we will also struggle for a solution. But be prepared to be skeptical. You will be driven to the extremely remote ranges, a way beyond anything we hope any direct access. Nevertheless, arrow of time is a fact of the nature and deserves an explanation. As a layman, we know time has a direction. The direction in which we age. We are accustomed to many one-way processes, that is, process that can occur only in a certain sequence, that is the right way, and never in the reverse sequence, that's a wrong way. An egg dropped onto the floor, a pizza is baked, a car is driven into a lamppost, a large wave erode a sandy beach. These are one-way processes which are irreversible, meaning that they cannot be reversed by means of only small changes in their environment. One goal of physics is to understand why time has a direction and why one-way processes are irreversible. Although this physics might seem disconnected from practical situations of everyday life, it is in fact at the heart of any engine, such as a car engine, because it determines how well an engine can run. The key to understand why one-way processes cannot be reversed involves a quantity that is known in physics and science as entropy. When we are adding coffee powder in the milk, the mixing becomes an irreversible process. By any method, we cannot segregate the coffee powder back. That is an irreversible process that we experience every day. I'm your instructor, Dr. Shyamkant Anwane, Professor and Head Department of Physics, Sri Shivaji Education Society, Amravati Science College, Nagpur. Let us delve into the issue of entropy. In this video entitled What is an Entropy, the discussion will flow through following key points. The warm-up example may be skipped by beginners, amateurs, and advanced learners if they wish. When we delve deep into the issue of entropy, we encounter with the literature carrying entropy postulate. If an irreversible process occurs in a closed system, always increases the entropy of the system. Entropy never decreases. The changes in energy within a closed system do not set the direction of irreversible process. Rather, that direction is set by other property that we shall discuss here as entropy, capital S, of the system. The change in entropy of the system is defined later in this module, but we can here state its central property, often called entropy postulate. Entropy differs from energy. Entropy does not obey conservation law. The energy of a closed system is always conserved. It remains constant. For irreversible processes, entropy of a closed system always increases. Because of this property, the changes in entropy is sometimes called the arrow of time. For example, we associate the explosion of popcorn kernel with the forward direction of time and with an increase of entropy. The backward direction of time, a video you can play in the reverse direction, would correspond to explode of popcorn reforming the original kernel. Because this backward process would result in entropy decrease, it never happens. There are two equivalent ways to define the change in entropy of the system. Number one, in terms of system's temperature and energy of the system gains or loses as heat. Second, by counting the ways in which atoms or molecules that make up the system can be arranged. Here you can see a puddle of gas inside the room, and with time the distribution tends to become homogeneous. However, we can never do any process that reverses the present situation to the initial situation. What does Earth get from Sun? Pause this video and ask yourself. The Earth receives several vital forms of energy and influence from the Sun, which makes life and natural processes possible. Here's what Earth gets from Sun. You can see. Number one, light, visible radiation, heat energy, ultraviolet radiation, solar wind and magnetic influence, foundation of all energy on Earth. This is what we get from Sun. The next obvious question is, what does Earth retain? Again, pause the video and try to answer. That is a brainstorming question. Out of all energy received, about 20% is absorbed by the atmosphere, like clouds, water vapor, dust absorb solar radiation. Let us try to figure out answer to this question. What does Earth retain? This is a magnificent question. I believe you pause your video and try to figure out what does Earth retain. I'll explain you. Out of the total energy received, 20% is absorbed by the atmosphere, while 50% is absorbed by the surface and 30% energy is reflected back. Albedo, that is reflection from clouds, ice, snow and desert. What is retained? This question is still unanswered. So overall, what does Earth gains? What happens to the retained 70% energy? It warms land and ocean, evaporation, wind, weather systems are driven. It powers photosynthesis in plants. Eventually, this energy is re-radiated as infrared radiation. Note down, infrared radiation. Some escapes to space, some is trapped by greenhouse gases, and Earth is maintaining its average temperature of 15 degrees centigrade. So inflow energy is equal to outflow energy, and the gain is nothing, no gain. Whatever is absorbed, accepted, is re-radiated back in the form of infrared radiation mainly. So our takeaway of this slide is, what Earth gains from Sun is nothing. However, the life is sustainable on this planet only because of Sun. Entropy plays a very key role in this process that we'll try to unfold in coming slides. Many a times history is, interesting and inspiring also. Sadi Carnot was born in Paris on the 1st of June 1796 at the Petit Luxembourg Palace, where his father Lézard resided as one of the 5 members of the Directory, the highest governing body of French First Republic. Sadi was named by his father Lézard after 13th century Persian poet Sadi of Shiraz. He analyzed how heat, that is thermal energy, can be converted into work, that is mechanical energy. He introduced the concept of idealized heat engine, now called as Carnot engine. He defined Carnot cycle, a theoretical model that represented maximum efficiency of a heat engine that can be achieved between two temperature reservoirs. Carnot's idea laid foundation of second law of thermodynamics. He showed no engine can be more efficient than Carnot's engine operating between the same two temperatures. His idea helped the later scientists Clausius and Kelvin to develop the modern concepts of entropy that we are going to learn now. If you are novice, I'll quickly explain the Carnot cycle, the idealized heat engine. The Carnot cycle is a theoretical thermodynamic cycle proposed by Sadi Carnot in 1824 that defines maximum possible efficiency of any heat engine operating between two temperatures. It consists of 4 irreversible processes, 2 isothermal processes, that is operating at constant temperature, and 2 adiabatic processes, that is no exchange of heat, steps through which an ideal gas is taken cyclically. The 4 stages of Carnot cycle we shall go through. The first one is isothermal expansion from 1 to 2. You can figure out in the diagram. On y-axis we have pressure, which is dependent variable, and on x-axis we have volume. So when we are following from 1 to 2, the pressure is going down and volume is increasing. That process 1 to 2 is isothermal expansion, and this piston, you can locate the gas in the cylinder, and this piston will go up in the isothermal expansion process. The gas expands at a constant high temperature T1 as it absorbs Q1 amount of heat from the heat reservoir. It absorbs heat Q1 from hot reservoir. The gas does a work on the surroundings. Second is 2 to 3, that is adiabatic expansion. The gas continues to expand but without heat exchange. Its temperature falls from T1 to T2. The internal energy decreases as the work is done by the gas. The third process is 3 to 4, isothermal compression. The gas is compressed at a constant low temperature T2. It releases heat Q2 to the cold reservoir. The work is done on the gas. And the fourth stage is while moving from 4 to 1, that is adiabatic compression. The gas is compressed without heat exchange, rising its temperature back to T1. The system returns to its original state, completing the cycle, making it completely reversible. The efficiency of the Carnot engine we can define by 1 minus T2 upon T1 or 1 minus Q2 upon Q1 in form of temperature and in form of heat. So you can have a look at the efficiency formula in form of temperature of hot reservoir minus temperature of cold divided by temperature of hot. If you multiply this fraction by 100, it will be percentage efficiency. If you like in form of the heat absorbed and evolved, you can find out the efficiency effectively, and we shall explore this for a particular situation when the cold one is at 20 degrees centigrade and the hot is at 160 degree. One has to convert that into Kelvin and we can calculate the efficiency, which merely turns to be 32%. So here our takeaway are there exists an upper limit of efficiency for any heat engine. No real engine can surpass Carnot efficiency due to irreversibility and losses. This forms the basis of second law of thermodynamics and the concept of entropy. The efficiency eta depends on Th and Tc, and to reach to unity, Th must approach to infinite Kelvin temperature and Tc must approach to 0 Kelvin temperature. Both are impossible. With no friction and heat losses leading to ideal conditions, eta cannot be unity. With 20 degrees centigrade and 160 degrees centigrade practical conditions, after conversion we have seen eta to be 32%. After converting these temperatures into Kelvin, eta is 32%. Practically, the piston cylinder is heated and radiates heat, leading to the losses that cannot be recovered. Usable when, I mean to say, energy, heat energy, temperature is usable when concentrated and less usable when spread out. Clausius in 1865 concentrated in small portion, small entropy, and when entropy is spread out, entropy increases. It means same amount of energy is present but in dispersed form and not capable of doing work. So I'm going back to the first law of thermodynamics, energy of the universe is constant, and second law of thermodynamics, entropy of the universe tends to become maximum. In other words, energy spreads out with time. Hot things cool down, cold things heat up, gas expands on heating. Perpetual motion is impossible. Amount of usable energy in a closed system is always decreasing. The most obvious way to describe entropy is measure of disorder that we learn in school and colleges. The best way to think it as entropy is as a tendency of energy to spread out. Then the proficient question, the most prominent question is why does energy spread out with time? Without getting into the intricacies of statistical mechanics, I'll explain the term microstate and macrostate defined there. These are a description of two complementary levels of understanding of a physical system. One is microscopic, that is detailed understanding, while the one is macroscopic, that is observable. A microstate is a specific detailed configuration of a system describing the exact state, that is position and momentum, of each individual particle at a given time. It represents how the particle, or rather how the particles are arranged and moving in the microscopic level. Many microstates can correspond to the same overall appearance of measurable condition, that is a macro state. We shall discuss this issue with an example. The another thing I want to define is macro state. Now, macro state is defined by macroscopic quantities such as pressure, volume, temperature, then energy, that is total energy, properties that we measure experimentally in our laboratories. Each macrostate corresponds to a collection of microstates that share the same macroscopic properties. So, on micro level, we have molecules, atoms, electrons, protons, elementary particles, photons, and so on. Whereas in macro state, we consider a bulk solid, liquid, gas, radiation, and so on. In short, micro is on small dimensions. We look for individual properties of nuclei, atom, and molecules. Macro is a bulk property like electrical, thermal conductivity, specific heat, dielectric constant, pressure, volume, temperature that we are measuring in the laboratory. And I very quickly want to tell you the definition of statistical mechanics in a very rough way. It is the process, it is the mechanics that offers you relation about the macro state by some function which depends on microstate. So macro state is equal to function of microstate. And if we know the function, that we call the knowledge of statistical mechanics in short. So if someone is interested in statistical mechanics, can refer to my other videos. Statistical mechanics is the branch of science that establishes relationship between macroscopic properties in terms of microscopic properties, that is individual properties. As the name suggests, it does not concern with the actual individual motion interaction. Rather, it explores the most probable behavior. The principle of a priori probability again comes from statistical mechanics. For a given macro state, there exist large number of microstates. There can be one also, there can be more also, depends. All microstates are equally probable. So the number of macrostates is a different number. The number of microstates can be exponentially large as compared to the number of macrostates. And the principle of a priori probability states that all microstates are equally probable. Consider a closed system. In the sense, consider a glass vessel containing gas for statistical study. It will definitely have some macrostates and many microstates. Let us suppose that N1 particles possess E1 energy, N2 possess E2, so on and so forth. N number of particles possess En energy. If these particles are non-interacting, the total energy and number of particles of the system will be conserved and can be expressed as total energy is sum of N1 E1 plus N2 E2 and so on, and N1 plus N2 plus N3 and so on up to Nn will be the total number of particles. Now we shall deal with a nice a priori probability example with two cells having four particles being distributed, ith cell and jth cell. So the entire volume we have parted into left half and right half, and at the beginning we shall consider Ni, that is number of particles in the ith cell is 0 and number of particles in the jth cell is 4. So 0, 4 is the first macro state. Then we shall talk about 1-3 distribution, 2-2 distribution, 3-1 distribution, and 4-0 distribution. So here the number of ways in which four particles can be arranged in the right half, it is unique. So all A, B, C, D are in the right half, nothing present in the left half. Similarly, 1-3 distribution, one particle is in the left, three in the right. So A, B, C, D particles, first microstate pertaining to this macrostate will be one particle A, then it can be B, C, and D. So here there are four distinct ways of representing the second macrostate. Then third macrostate we shall talk about 2-2 distribution, then 3-1 and 4-0 again. Kind of similar, I mean to say. So if you like to distribute two particles in left half and obviously two particles in the right half, AB, AC, AD is the first possible combination. Then with B beginning, BC, BD is the second possible option. C beginning, D is the only option. ABBA we are not repeating. So there are only 6, rather there are maximum possible microstates, 6 for this particular distribution 2-2. And 3-1 similar situation will be prevailing with interchange of right and left. And for this also ABCD will be in the left half with nothing in the right half. Now this column is representing macrostate 1, 2, 3, 4, 5. So 2 cells, 4 particle, we have 5 macrostate, and for first macrostate we have only 1 microstate. For second macrostate we have 4 microstates. For the third macrostate, 2 particle distributions, we have 6 microstates, and here we can represent a series of macrostates on x-axis and microstates on y-axis. So this will be the kind of distribution for macrostate versus microstates, and all microstates are equally probable. That is the principle of a priori probability. So how many microstates are there? 1 plus 4 plus 6 plus 4 plus 1. So it will be 16. So all 16 microstates are equally probable. That is the principle of a priori probability. Now in our example, let us increase cells from 2 cells I and J to say 64 cells. On your screen you can observe a checker pattern 8 by 8 leading to 64 cells, and we have one ball, and we have to find the number of distinct ways of placing this one particle or one ball in 64 cells. Obviously the ways will be 64. It can be expressed by combination formula NCR, which is n factorial upon r factorial into n minus r factorial, and 64C1 will be simply 64. You can see the animation. So every point, every cell, when it occupies, leads to a distinct way of placing one particle into these 64 cells. So this is a warm-up example. Let us go through this warm-up example where we are increasing cells from 2 to 64, and we'll see what happens. Now let us suppose that we have same 64 cells with 2 balls. The number of distinct ways of placing these 2 particles in 64 cells we can calculate by combination formula, that is 2016, and here you can see one set of 63 combinations. Then the first ball we can displace to new position, this laser pointer location, and The rest of locations, which are again 63 minus 1, 62 in number, can be tracked, so on and so forth. We can raise 2016 distinct combinations. With 3 balls, these combinations lead to 41,664, and for 4 balls it is 0.6 million. Let us reach to a phenomenal number of ways wherein we have 64 cells with 32 balls, and on your screen you observe the most ordered pattern in which 32 balls are occupying left half and right half is completely empty. Now if you roll through the formula, you will be able to see a number at the bottom, very long number, which is 1.8 into 10 power 18 number of distinct ways. Mind it, it is the number of distinct ways of placing 32 particles in 64 cells. This table represents a wonderful data which encompasses how the number R when played. Number of balls, we are considering 0. Only one way we can represent that. If we consider 12 balls to be placed into 64 cells, and we are talking about number of distinct ways, they are phenomenal. 3.2 into 10 power 12. The highest possible distribution, 32 balls in 64 cells, is 1.8 into 10 power 18, as just now we have seen in the last slide. And this number again goes on decreasing, reach to unity, 64 cells filled with 64 balls. So this is how the distribution goes. This number is astronomical, 1.8 into 10 power 18. To look at these numbers, I prefer to talk in terms of log of NCR, that is 18.263. Now, this is a very interesting thing. Ludwig Boltzmann was an Austrian physicist who formulated statistical definition of entropy. His famous entropy formula, S is equal to K log W, actually K log to the base EW, is displayed on your screen. The Boltzmann's constant is shown as a key physical constant connecting microscopic particle behavior to macroscopic thermodynamic quantities. Here, the visuals represent molecular motion, energy distributions, and entropy diagrams symbolizing randomness, probability, and the microscopic basis of thermodynamics. The Boltzmann's legacy is linking microscopic physics to macroscopic thermodynamics. So here I want to mention that this W is called thermodynamic probability, or the number of microstates, which we are representing here as NCR. This table actually represents log to the base 10, and in this formula we are using ln, that stands for log to the base E. Boltzmann's legacy is in linking microscopic physics to macroscopic thermodynamics, the statistical nature of entropy and order disorder in the systems. One of my friends, Professor Mahesh, recently visited this October 2025 the Boltzmann's grave in Vienna, Austria. Physicist epitaph provides final confirmation to a career of turmoil. Now, if this blue block is a kind of piston that compresses 32 balls into 32 cells. So that is the only one way we can arrange it. Alright. Now, if we consider 40 cells to be filled with 32 balls, now I am changing number of cells and number of balls 32 is fixed. So for this, the number of distinct ways, just by offering a column of 8, has increased to the order of 10 to the power 7. That is about 70 million distinct ways. If we add one more row, that is 48 cells with 32 balls, the number is 2.25 into 10 power 12. So on and so forth. Third column, if we add 8, 8 and 8, 24 free vacancies we have offered, leading to 32 plus 24, that is 56 cells with 32 balls. The number is increasing, 4.35 into 10 power 15, and this complete we have already discussed. So what is happening, as we are compressing the gas, we can reach to the most ordered state, and it has a unique combination. If we are talking about 64 cells and 32 balls, we have 1.8 into 10 power 18 number of distinct ways in which the balls can be arranged. Now, if we want to retrograde back to this ordered state, the probability will be not 0, but it will be close to 0. The probability will be disordered state number of ways is unique, 1 divided by 1.8 into 10 power 18, that is almost 10 to the power minus 18. So if this distribution is happening randomly, how much time it will take so that randomly we'll go back to the initial state, which is the most ordered state? It will be a very long time, to the tune of age of the universe, which we consider 14.7 billion years. It's not impossible, though it's not impossible, but it is having so small probability that it will take age of the universe time to randomly reach back to that ordered state, which is unique of its kind. So entropy of the system, it is very less probable that it will go back to the ordered state. Instead, it will be ever increasing, because the number of permitted combinations are 1.8 into 10 power 18. This I am talking for simple situation wherein we have 64 cells with 32 balls. Now if you take a real size room and a puddle of gas like 1 mole substance, which is Avogadro's number. So if R is Avogadro's number to the tune 10 to the 23 and total number of sides sorry, with reference to the room, then the number of distinct ways will be enormous. Here I want to summarize the last discussion, wherein the number of sites, if they are restricted to 32, and the number of balls we have already restricted to 32. So that is the unique way of placing. 32 balls in 32 sites. Then when we open 8 more cells option with same 32 balls, the number of distinct ways will be 76.9 million. When we increase the number of cells again by only 8, the number of distinct ways is 2.25 into 10 power 12, and so on and so forth. So here you can observe, if we sum together the total number of ways for all these combinations, it is 1.8 into 10 power 18. So now we can calculate the probability of occurrence of the most ordered state. So 1 divided by this total number, this leads to 5.4 into 10 power minus 17. So it is absolutely less probable. Not 0, but 10 to the power minus 17 is very small number. Whereas when we go on increasing the number of cells to 64, the number of distinct ways in which we can place that is 1.832 into 10 power 18, and this number divided by the total number, this offers probability 100% almost. Let us consider a case of pouring milk into coffee powder in a mug. Okay. Now here we shall talk about the macrostates and microstates in a nice way. Consider a cup containing only coffee powder that makes an ordered state, low entropy, small entropy. Then after pouring milk, the mixing begins, and finally it is completely mixed. So these are the three macrostates for our consideration. The corresponding microstates you can assume the case we have done earlier with 64 cells and 32 balls. You can relate it to 32 coffee powder grains. Now, when there is no milk in the cup, all coffee powder is segregated in the bottom. It is lying in the bottom. So that leads to an ordered state wherein we do not allow the particles to climb up. Then we allow some mixing by pouring milk, and by completely introducing milk, it is allowed to undergo a complete mix. So number of ways of distribution, we have already learned that in the first case, this is the most ordered state, and the number of distinct ways in which it can be done is 1. Whereas when we open one row of 8, in this case, the number of ways is about 76.9 million. And when we allow another 32 cells, the number of ways are phenomenal. That is 1.8 into 10 power 18. Now, the probability of occurrence of this initial state after getting this complete mixture, the number of ways of this microstate, all microstates are equally probable. So here the chance is only 1 out of the total chances 1.8 into 10 power 18. So 1 upon 1.8 into 10 power 18, this number will be phenomenally small, almost 0. In this case, we have about 76.9 million ways, but they are also very small as compared to this phenomenal number 1.8 into 10 power 18. And in the third case, we have 1.8 into 10 power 18 total ways, divided by, these are the number of ways divided by total number of ways. So this is unity. So this is most probable. So this state is most probable. Here I should have shown this balls getting mixed everywhere. Once again, come back to the example of coffee being mixed into milk. The first stage is of lowest entropy, wherein the coffee powder is segregated in the upper half in this picture, whereas milk is residing in the down part. So the mixing begins. It evolves with time. So here entropy is higher, and here the entropy is highest. The number of probable ways of mixing these coffee particles is outnumbered. Therefore, the entropy is high. Technically, reversibility is not impossible, but chances are astronomically small. One may need eternal time of waiting for it to happen. Like you can say, like the age of universe, 14.7 billion years. So the ordered state means less number of microstates. The disordered state means a large or a very large microstates. On micro level, you can not say that the evolution is going forward or backward in time, because all microstates are equally probable. That is the principle of a priori probability, as all microstates are equally likely. So the arrow of time is not coming from physics. That is very interesting. It is actually coming from statistics and probability. So entropy of a closed system always increases. The reason behind that is a large number of microstates corresponding to the given macrostate. If you consider on life scale this example of mixing coffee powder into the milk, we consider coffee powder particle equal to 6.02 into 10 power 23 per mole in 1 gram. This is the small amount of coffee we are adding, and the number of sites available in the glass of milk is very large as compared to the number of coffee grains. And NCR here, you imagine R to be Avogadro's number, and small n, I mean this one, small n is very large, and this R is Avogadro's number. So NCR, it will be extremely large quantity. The most ordered state, which is unique, will be almost improbable, because that probability will be 1 upon NCR. Here 1 represents the ordered state. The moment you are adding coffee into the milk, and NCR is a huge number. Now let us consider a silly question for discussion, and probably that kickstarts your thinking. We have some gas filled into the container, and here on your screen you can observe red dots indicating gas molecule. Now the system has some entropy, you already know, and if we compress the gas to the lower portion of the vessel, then what do we envisage regards entropy? Entropy of the system is decreased, you feel. Can we do such an experiment to reduce the entropy of the system and violate the second law of thermodynamics? Pause this video, think, and generate your answer. I'll explain you, it will not decrease entropy of this closed system, because the moment you compress this particular gas in the vessel so that it reaches to the ordered state, the energy, the temperature of the system increases, it doesn't remain constant. And this temperature is out of the thermal energy, and the thermal energy can be distributed amongst these gas molecules in number of different ways, and that distribution has high entropy. So here, even if you feel you are reaching to ordered state apparently, but it is not. This thermal discussion is very interesting. I'll elaborate one more example to relate the entropy and temperature. Now let us consider a piece of metal. This strip I shall call A, and in this strip I am having 10 atoms, or you can say lattice positions, and here you can add energy, a bundle of energy to each atom. And for example, what I am doing, I am putting same bundle of energy and providing it to every lattice point. So in this way, you can consider that the metal strip A, which is composed of only 10 lattice points, is heated up, and every lattice point is vibrating about its mean position because of the thermal energy. And then we have another strip of metal, let me call that as B, and this is at low temperature, it is cold. Now what we do, we make a connection between A and B so that heat can flow. So what will happen, these bundles of energy will travel from A to B. That is what we have learned in school. That is what is happening. That is what we have seen during our Newton's law of cooling. Now, 5 energy bundles are in strip A, and the metal strip B also carries 5. So here the equilibrium will be attained. Now if you try to pass one more bundle of energy from A to B, will it be permitted? Practically not. Why? Because the heat will not flow between equal temperatures. And here what is happening? The temperature of A is reduced below the mean value of A and B is heated up. This is not, last is not permitted. The principle that heat flows from high temperature to low is an expression of second law of thermodynamics. More specifically, it relates to the concept of the direction of heat transfer. A bundle of energy, that is quantized unit of vibrational energy because of the thermal energy, is arising from the collection of oscillations of the atom in the crystal lattice. It represents the quantum of thermal energy in solids. If the bar carries one bundle, for example, R is equal to 1, will possess one unit of energy, for example, and the number of distinct ways in which this bundle of energy can be placed in the 10 lattice is 10. We have done this. So when R is equal to 1, for N is equal to 10, NCR is 10. So there are 10 distinct ways in which this bundle of energy can prevail in the crystal. Now, the maximum possible ways are for 5-5 distribution. So 5 R is equal to 5 means number of bundles of energy here will be 5, and obviously the remaining are in B. So here 252 out of the total number of ways 1024. So if you talk about probability, so probability of having one bundle of energy out of 1024 is 0.98%. This is maximum at r equal to 5. So here this is a graphical representation of the same thing. So this is most probable distribution, and the imbalanced ones are less probable, and their probability goes on reducing to the extent that the extreme ends are at 0.1% probability. Now 0.1% probability is a low entropy state, either for r equal to 0 and r equal to 10, whereas the most probable distribution is 5 bundles of energy in metal bar A as well B. When we start with 10 energy bundles in metal strip A and connect it thermally to B, so it is quite probable that we will have 5 energy bundles in metal strip A and 5 in B. Now consider n to be 100. It means that in metal strip A we have 100 lattice points, and in metal strip B also we have 100 lattice points. And then in the metal strip A, if you want to place 10 number of energy bundles, the number of distinct ways will be 1.73 into 10 power 13. If you want to distribute 50 energy bundles in 100 sites in metal A, the number of ways will be 1.01 into 10 to the power 29. So here the probability of this distribution is 84%, unlike to the earlier probability of 50-50, 24%. So for finding probability, we have taken the total number of ways, sum of this column here, 1.28 into 10 power 29. So 1 divided by 1.28 into 10 power 29 will be almost 0, and this probability is 84%. Now if we scale this number from 100 to 1000, that we'll see in the next discussion. First of all, what we'll do, we'll connect metal strip A with B. When the metal strip A has 100 lattice points and 100 energy bundles, metal strip B has 100 lattice point and all energy sites are vacant. They are thermally connected. What will happen? The energy bundles will flow from higher temperature, that is A, to B, and the macrostates will be like in this table. So metal strip A will have 100, B will have 0. These are beginning. As time flows, the flow will go towards B and it will be restricted at 50-50. It will not flow beyond this because heat flows from high temperature to low temperature. And why that is happening? The probability number is playing an important role. Here you can see, if we consider 1000 lattice points in metal strip A, then the number of ways in which 100 bundles of energy can be distributed is 10 to the power 139. So as you go on increasing this number to 500, the most probable distribution is 2.7 into 10 power 299. And if we sum together this number, This gives the total number of distinct ways for all macroscopic states. And for this particular 50-50 distribution, we have almost 100% distribution. So for n equal to 10 it was 24, for n equal to 100 it was 84, and for n equal to 1000 it is 100%. So in this chart you can see that the most probable distribution is at 50-50 in this case, where we have 1000 lattice points and 500 energy bundles in metal strip A. Under this situation, when we have 1000 lattice points in metal strip A, 1000 energy bundles in metal strip A, and B has 1000 lattice points and 0 energy bundles, and they are thermally connected, then the probability of occurrence of 50-50 distribution of energy bundles, that is 500 in A and 500 and B, will be most probable. In the real world problem, this number n, which we have raised from 10 to 100, 100 to 1000, and now we are going for 6 into 10 power 23 number, that is Avogadro's number per mole substance. And under this condition, we have one hot object, another cold object, and they are thermally connected to each other. Then their 50-50% distribution, that is heat will flow from high temperature to low, is most probable. In case of 1000 n equal to 1000, it is like this. In case of this Avogadro's number, this population will be actually highest. So when small n, that is number of sites, is equal to the Avogadro's number, and the disordered states are so astronomically large that the system rattles through it without returning to the least probable, which are ordered states, though it is not impossible, but very less probable. One needs to wait for long time, like age of the universe, which is impossible. So what is takeaway of this particular discussion? That heat flows from hot to cold. Heat flows from cold to hot is not impossible, but it is improbable, very less probable. Then the next question is how air conditioner is taking away heat from the room, making it cool and heating outside environment. A refrigerator is also doing the same thing. How that is happening? That's a question. Pause the video and think over it. If the energy naturally tends to spread out and make systems more disordered, how can we have something like air conditioning where the cool interior of a house gets even cooler while the hot exterior gets hotter? The energy seems to flow from cold to hot, apparently decreasing entropy inside the house. But the local decrease is only possible because the greater increase in the entropy occurs elsewhere. At the power plant, concentrated chemical energy in coal is released, hitting the plant and its surrounding, driving turbines and generators, hitting transmission line wires, and creating waste heat. The entropy reduced inside the home is vastly outweighed by the entropy produced to make that cooling possible. If the total entropy is always increasing, why does structure still exist like on Earth? Why are there hot and cold regions or even life? Because Earth is not a closed system, it constantly receives low entropy energy from the sun. Solar energy arrives in a highly ordered form, which plants capture to grow and produce sugars. Animals consume this energy to live and move, and the larger animals feed on the smaller ones. At each step, the energy becomes more dispersed and the entropy increases. Ultimately, all solar energy absorbed by Earth is transformed into thermal radiation and emitted back into the space, rather radiated back to the space. However, for each high energy photon we receive, Earth emits back around 20 low energy photons, a clear measure of entropy increase. Without this constant input of ordered energy and a way to release disordered energy, life would be impossible. In fact, life itself may exist because it helps accelerate the universe's natural tendency towards greater entropy. Living systems are exceptional at turning concentrated low energy into dispersed high entropy waste. So where does sun gets its low entropy energy? The answer lies in nuclear physics, where we are talking about fission and fusion. But originally it is from universe. Entropy has been increasing since the Big Bang, meaning it was once far lower. Immediately after the Big Bang, the universe was hot, dense, and uniform, apparently a high entropy state. But considering gravity, it was actually a very low entropy. Matter evenly spread out is extremely improbable under gravity, making that early state one of minimal entropy. As the universe expanded, matter clumped into galaxies and stars, releasing potential energy as heat, increasing its entropy. From this process arose stars, planets, and life. If the universe has tendency to spread out the energy, life has tendency to accelerate this process. The past hypothesis says that every day the entropy is increasing. At the time of Big Bang, it was lowest. Gravity compels all matter together. The arrow of time is in the direction of increasing entropy. Stephen Hawking said that the universe is expanding, and after some time this expansion will stop and there will be a big crunch, that the activity opposite to that of Big Bang, that is big crunch, in which everything will collapse back. During this time entropy will decrease and the arrow of time will be reversed, and the life will not be sustainable in that situation and will not be there to ask question what is happening. In 1972, Jacob Beckenston proposed that the black holes have entropy proportional to their surface area. Though initially doubted by Stephen Hawking, later proved that black holes emit radiation, now called as Hawking radiation, and then have both temperature and entropy. The supermassive black hole at the at the center of Milky Way holds about 10 to the power 91 Boltzmann constants worth of entropy, more than 1,000 times the entropy of early observable universe. Collectively, all black holes account for the most entropy in the universe today. So with this, we'll conclude our discussion. Thank you very much for your attention.